Okay, this is the presentations I did for 128 and 131 for section 5.2, chapter 5, section 2 of the text. So here's the preview activity that I went over. And so it says, find the area under this graph from 1 to x. Now, and it says compute a of 1. Well, if we find the area under any graph from 1 to 1, 1 to 1 has no width, and so the area would be 0. So a of 1 has to be 0. Now, a2, we can do it a couple of ways. First of all, we could just draw f of t, which is a line, goes through plus 4, and has a slope of minus 2. And so it looks like this, or that's 2 and that's 4, and the area between 1 and 2 would be this, which is 2 high, height of 2, and 1 wide. So the rectangle would be 2 times 1 is 2, but this is half, so it would be 1. So a of 2 should equal 1. Now we can also find the antiderivative of this using fundamental theorem of calculus. And then use the fundamental theorem of calculus to get this. So this is from 1 to x. My pens are messing that up a little bit. So the fundamental theorem of calculus, the antiderivative of 4 is 4x. The antiderivative, or t, I guess, since the variable is t, dt. And the antiderivative of negative 2t is negative t squared, because I raise the power by 1 makes it 2, and divide by 2, and so that cancels the 2. And we evaluate that from 1 to x, so we put 1 in here, and we get 4 minus 1. Oh, we put x in first. 1 to x, we put x in first, so we get 4x minus x squared. Get on autopilot and forget what I'm doing. Minus, and then we put 1 in, and we get 4 minus 1. So this would be the function a of x, and we're supposed to put in 2. So 4 times 2 is 8, minus 2 squared is 4, and 4 minus 1 is 3. So we have 8 minus 4, which is 4, minus 3, which is 1. So a of 2 equals 1. Okay. Use the first fundamental theorem of calculus to find a formula for a of x. Well, we just did that right here. If we just leave it x, so this is what it would look like, which is 4x minus x squared minus 3. Observe that the function is f is linear. This is linear. And what kind of function is a? Well, it's a quadratic. It's 1 degree higher. We talked about that in class. Use the formula you found in B that does not involve integrals to compute a prime. Well, the derivative of this would be 4 minus 2x squared, 2x to the 1, because we take the derivative of that, and the derivative of that's gone. So it's 4 minus 2x, which is what this was. except this had t and now this has x. Now, we could have guessed that that would have been, since this is x, we could have put it just in place of the t and called it 4 minus 2x, which is what it worked out to be. And we didn't use integrals, we found the derivative that way. So, they defined f of t as 4 minus 2t. It is equivalent to say that f is given by f of x. That's what we just said. What do you observe about the relationship between a and f? F is the derivative of a. A is the area under the derivative. And that's the relationships they wanted you to see in that. In the preview activity. So that's stuff we've already kind of looked at before. Now this says the second fundamental theorem of calculus. All right. So the area under this graph, the area is given, and that this is the area from 2 to someplace else x. That area increases or decreases as you move along, and they're making that a function. Now, something important to see is that a of, if we go from 2, so that we're doing the integral from 2 to 2, that has to be 0. Because if you have no width, the integral has to be 0. The area is 0. Okay? Now, so they say that up here, we can determine a formula for that by doing the first fundamental theorem of calculus. Specifically, do the antiderivative of this. Well, the antiderivative of cosine t is sine t. The antiderivative of t is 1/2 t squared, evaluated from 2 to x. And so we put x in and we get this part. And we put the 2 in, we get this part. And we would get this as the a of x. Now, if you took the derivative of this, so you take the derivative of this, we'd get cosine of x, and 2 times 1/2 is 1, x to the 1, and the derivative of the constant is 0, so this is the derivative of all of this stuff. So the derivative of a of x is just the original thing with the x put in for the t. And so a prime of x is just f of x, but we had f of t, but now it becomes f of x. Because a of x is a function of x, and this is x. And a of 2 has to be 0, like I said earlier, up here, because if we go from 2 to 2, we have to get 0. Okay. So then, we looked at, this one. Got these out of order here. Next thing we did, and this is on today, on Monday, the 31st, we looked at this one. And I asked the class to just graph this. Graph y equals e to the, and I said make it negative x squared. And so, what does that look like? So we put it in the calculator, and it looked like, let's see what it looks like here. I'll put it in my calculator, show it to you, and then I'll kind of sketch it on. E to the negative of x squared. And I'm going to zoom 4. Okay, so it gets up to 1, And by 1, it's down to here. And then by 2, it looks like it's basically 0. And same thing on the negative side. It's symmetric. So it's down to about there, and it's already down to 0. So it looks something like this. Okay. Well, e of x, which we're trying to get a handle on, is, and I'm going to draw that here. Now, e of x is the area from 0 to x on this graph. Now, remember, this was in terms of t. For the calculator purpose, we had to make it x, but this is t. So how far we integrate, how far we add up the area from 0 to some place is what this is the variable. So we're adding up the area under this. So what's e of 0? Well, the integral from 0 to 0 has to be 0. There's no width. And if we look at this, if we go from 0 to 0 under this, you're going to get no area. So e of 0 has to be 0. Now, what's e of 1? Well, that would be the area under this curve from 0 to 1. So from here to there, the area. Well, that looks like it's 0.75 maybe. So by 1, it must be 0.75. Now, I'm going to go to this the calculator and actually calculate it more accurately than my rough sketch here. So second, calculate the area from 0 to 1. And it says 0.746. Oh, well, that's 0.75, so I did pretty well on my guess there. Now let's get to 2. Well, we're adding a little bit more area. Let's see, that might be 0.1 or 0.2, so that would add to this. So e of 2, adding this to this, I might get like 0.85 or something. Let's find out what it is. So second, calculate the integral 7, and it's starting at 2 and going to 1 and going to 2, and that added 1.35, 1.4 to this, so that would be 9-ish. So at 2, it's got to be 0.89. And after that, it doesn't look like it adds much area, so it must go there, there, and then kind of level out. Okay? Now, what happens on the other side? Well, this is positive area, so it was increasing, and it had to be 0 here, so it had to go from below, and so it must have been at -1, it must have been negative 0.75, and at -2, it must have been negative 0.89, and after that, pretty steady. And so it looks something like this. Now let's talk about the curvature. So now, instead of looking at the area to make the height of this graph, we're looking at the slope of this graph, which would be the second derivative of this, and that tells us the curvature. And the slope is negative all the way through here and all the way out here. Negative slope, and so it's got to be curved down. So all of this is curved down. Now over here, the slope is all positive, so all of this has to be curved up. And so this is roughly what e of x looks like. Now I never did find the antiderivative of this and then plug x into it and 0 into it. I just did it from looking at the area under this curve. And so we can find a function of x based on the area of another curve. So that's basically what they went through here on this, saying, and e prime is the derivative of this, and talked about the slope and all the different things that are going on. But that's basically what I want you to be able to understand from 5.2.3 example. Now, activity 5.2.3, and we're going to be doing basically the same stuff. They provided a graph down here for us to graph on. So I'm going to make it 1 and 2 and 1 and 2 and 3. They asked us to go to 10, but I'm not going to go that far. It gets rather boring out there. Okay. So the first thing they said, let's graph that. That's t over 1 plus t squared. So f of t is t over 1 plus t squared. So if I put in 0, I get 0 over 1, which is 0. If I put 1 in, I get 1 over 2, which is 1/2. If I put 2 in, I get 2 over 5, which is 2/5 or 0.4, so it's a little less than a half. If I put 3 in, I get 3 over 10. 3/10 is 0.3, which is somewhere like there. Okay. And if I put -1, the denominator is going to stay positive, but the numerator is going to change to negative. So I'm going to get the same numbers, but on negative side. 1/2, 0.4, and 0.3-ish. And so I have to draw something that goes like this and to this. So let's take a look on the calculator what it actually looks like. So clear that, and we have alpha y, we get a fraction, and it's x over 1 plus x squared. Now, it's not really x, it said t, but for the calculator we have to do that. And if I do trace, you can see at 1, it's 1/2. At 2, it's 2/5. At 3, it's 3/10. And 4/17, and it keeps going down. But it's a nice, smooth, bendy curve. So, looks like this. And it reaches a kind of a maximum, a local maximum at 1, and a local minimum at -1. Okay? So, what's f prime, which is the integral from 0 to x of this? F of x, capital F of x. Well, I'm going to ask you what f of 0 has to be. And so if this is 0 in the x, 0 to 0 has to be an area of 0. So it has to go through 0. And now I'm going to estimate the area off this graph. And so if this is 1, this would be half. So this looks like less than half, like maybe 0.3 by 1. And that's how much it goes up by. And then it looks like it might go up by another 0.3, so it might be at 0.6 east by 2. And then it goes up by more, maybe 0.2, so it'd be 0.8. And maybe a little bit more, and it's creeping up. Let's see if we can get those values. So on second calculate, 7 from 0 to 1, and we get 0.34. That's how high it should have been on here, 0.34. And second calculate, 7 between 0 and 2. So we added some more to it and got up to 0.8, it says. So we should have been a little higher here than what I estimated. And now let's go from 0 to 3 to find f of 3. So f of 1 was, what was, I forget, f of 2 I still have is 0.8, 0.3 something. And f of 3, by going second calculate the area from 0 to 3, and that's 1.15, so it's a little over 1, higher than what I had. And there's still area being added, so it's going to kind of keep going up, but not a lot. Okay, now I'm going to retype the X so it regraphs and gets rid of that shading. So this is all positive area, so it means this graph is increasing. And this is a positive slope up till 1, so that means it's got to be concave up. Then after that, it's got a negative slope, so it's got to be concave down. Now, I had some students ask me, how can a function continue increasing if it's concave down? Well, it can be something like this, getting flatter and flatter and flatter, but curved down. Now, let's go to the negative side. This is negative area, so this function has to be going down, but it has to end up at 0, so it must be positive here and coming down. And it looks very similar, and so this is probably a reflection over, and that's exactly what it is. So 0.3, 0.8, and f of 3 was 1.2-ish. 1.2-ish, and so this looks like this, and negative slope, so it's concave down, and then positive slope for the last unit. So it's concaved up there, and then concave down the rest of the way. So there's a picture of f of x. Now let's see if we've done what they asked for. On the axis, plot this. Did it. They said go from -10 to 10. I didn't do that. This is so small, I wanted to see it a little better. So I made it larger. What is the key relationship between f and f little f? The area under little f is big F. Or, if you will, the antiderivative of little f is big F. Those are both key relationships. Then it says the first derivative test. Now remind yourselves of what the first derivative tests. The first derivative is what we graphed here. Since that's the antiderivative, that's the first derivative of this. And the first derivative, if it is a positive value, so if it's above the x-axis, like 0.5 or point something, or 0.2 or 4, whatever, if it's a positive height, this graph has to be increasing. Because remember, these are the slopes. 0.5, a slope of a half. A slope of a 0.4. A point less. 0.4 or 3 getting less. So The first derivative says if this graph is showing the slope, that's telling you what this is. If it's positive, it's increasing. Here they're all negative. They're all below the x-axis. So this function has to be decreasing. So the first derivative test, because this is negative, means this has to be decreasing. And since this is positive, means increasing. That's the first derivative test. Then it says, what about the second derivative test? Well, the second derivative test is looking at concavity. The first derivative is this, and the second derivative is the slope of this one. So the slope here is positive, and the slope here is positive. The slope is m is greater than 0. Slope is positive. M, like in y equals mxb, slope, is positive, which means over here it has to be concave up. From here to here. Concaved up. And then here the slope is negative. And over here the slope is negative. And if it's negative slope, this means it must be, since the slope of the derivative is the second derivative, and the slope is negative, so it is concave down. So that's what they mean by second derivative test. Now they did something else here and figured out the second derivative, but it's just the slope of this. So we don't need to graph that. We can just look at the slope on this and tell what the second derivative test is going to do. And then it says use technology to find f of 5 and f of 10. So you would use this and go second calculate the area from 0 to 5, and it says that is 1.62. And f of 10 I'd have to graph further out, so I'd have to go zoom 6, which makes this all smaller and hard to see, but then I can go second calculate the area from 0 to 10. F of 6 allows us to go to 10. Gets clear out there, and we get 2.3. So by 10, this is up to 2.3. So it does keep going up. Here's 2. By 10, it's above that line. So it's going up, going to get up there. Okay. And then sketch the graphs. And we did that. All right. Let's see, we did. So, this is the rest of the example that we had just a little bit ago that I did earlier. Not the preview activity, not the, yes, this one. And here's what they came up with for the graphs. They zoomed in a little closer than we did, and they got this picture and that picture. And I'm missing the last thing that I did in class here, so I'm going to have to pause this,